Hey, good day, guys. You're welcome again to my channel. I am Joshua the designer, and in this video, I'll be showing to you how to design um, a single span T-beam. All right, so before this video you're seeing currently, I have made several other videos on the design and also detailing of several structural elements. But just to bring perspective to beam detailing that we started already in my previous video, I want to show to you how to come about your design of the beam element. All right, so I'll be using a single span T-beam, a typical example of such, to teach you how you can go about it. So this is a question on your screen on my left, and you see this says a floor system consisting of a solid in situ reinforced concrete slab cast integrally, all right, with the support beams is simply supported over a span of 6 meters as shown in figure 5.74, which is the figure below this question. So we have the design data. We have the dead load, we have the imposed load, we have the concrete grade, we have the characteristic strengths of reinforcing steel, we have the exposure conditions, and we have the fire resistance, slab thickness, rib width, overall depth, span of main beams, and center of main beams. All right, all these informations are necessary for us to carry out our design procedure. And also, in doing these things, I'll be showing to you how we pick references from the BS 8110 for our designs. All right, so you must have, alongside this present design, you must have BS 8110. This is mine, so I'll be showing to you how I will be going through this document and picking references from it. All right, so to go back to our design now. So the question says already that we are supposed to design a suitable reinforcement for a typical T section. All right, so and a T section, you know already that it is different from a rectangular beam section, so the approach will definitely be different. Okay, you can see it's even in a bold letters. So the first thing you want to do is to calculate or determine your design loadings. All right, or you call it your beam loadings. All right, so to do that, many things come together to characterize your beam load, both for the dead and the life load. All right, so let us just spell them out and go about all these things step after another. So the first thing we will do is to determine our slab loadings, because the beam is also going to pick up the load from the slab. All right, so to start with, we have our loadings, and it's going to be our slab loadings. All right, so the first thing to do is to obtain our slab loadings, because the load from your slab is going to be transferred to the beam. All right, so that's a system with which we transfer our load down to the bearing strata. So the slab loading, now we have the slab own weight, and we have the thickness of the slab from the question to be 0.16. All right, then multiply by 24. Density of concrete, then we have 3.84 kilonewton per meter square. All right, we have the finishes. All right, the finishes, which is also 1.0. That's from the question. Characteristic dead load excluding self weight. All right, and that's why we had to calculate our self weight. Then the other one that makes up the dead load, in addition to the self weight, is the finishes. So we've done that already. So, and also we are to have our total. This forms our total dead load. All right, total dead load, and that will be 4.84 kilonewton per meter square. Then we have our live load, which is the same thing as imposed load, as given in the question. Imposed load QK, all right, is 5.0 kilonewton per meter square, as given in the question. All right. So the next thing to do now is to get your ultimate design load, all right, that is going to get into your beam when you're loading it, all right. So, or you can leave it this way, so that the load from your slab, if you're considering a central beam, we have a lot of intermediate beams, for example, as the figure has shown to us. Let's assume we have this. For example, we have a slab we have slabs which are 4 meters away from the support, or 4 meters apart, the support 4 meters apart rather. All right, so to get the load that will be transmitted to an internal support like this, is going to be half of this span and half of this span, which would give us a total of a full length. All right, so that's exactly what we want to do here. So we have something like this. Let's just pay attention. On our beam, on our slab now, we have a load, a dead load of 4.84 kilonewton per meter square, and we have a live load of 5.0 kilonewton per meter square on that same arrangement. Now, if we want to transfer this to our beam, all right, because our beam, we have intention of designing a beam and not a slab, all right, so let's do that. For the beam loading now, the beam loading, don't forget that the first thing you are going to have is your self weight, the beam self weight. And if you check through the figure we have below, the dimension of our beam is 500 mm deep, or the thickness is 500 mm. So if we are subtracting the thickness of the slab away from the thickness of the beam, because we have already calculated the weight of the slab, all right, so we don't want to calculate the same thickness of slab when we are doing for the beam also. So we want to subtract the thickness of the slab from the overall thickness of the beam. So that will be 500 minus 160. All right, so, and that is why we would have that's why we would have 0.35, which is 350, 0.34 rather. All right, so you have 500 minus the thickness of the slab, that's 0.34. Then we multiply this by the thickness of that beam, all right, which is 350 mm, 0.35. All right, then multiply by 24. So that will give us 2.86 kilonewton per meter. All right, so to add the load from the slabs now, because we've done that for the self weight of the beam, so we want to add the load from the slab, all right, above the beam. So that's going to be for the dead load, because the self weight of the beam is a dead load. So we're going to pick the dead load from the slab and add it to this. All right, slab dead load, all right, to be transferred now will be 4.84 multiplied by 4. I hope you understand that now. I really hope you understand that. So that will give us 15.36 kilonewton per meter. 4.84 divided by, that's 19.36. Sorry about that. Now this is what I just did. Simply what I just did basically is to use this L to multiply the load that we have that's coming on that beam. All right, so what we have is saying is 0.16 multiplied by 4 multiplied by 24. All right, so that's 15.36 kilonewton. So we're good. Is it, sorry about that, not 15.36, that's 19.36, not 15.36, 19.36, 19.36. Oh, sorry, 19 is what I need here. 19.36. All right, so the dead load from the slab, I spread it across the portion with which the beam is supposed to support directly, and that's what we have. That's why we have 19.36. All right, so the next thing we want to have is the life load. So adding these two together should give me my total dead load. All right, should give me my total dead load, 19.36 plus 2.86, 22.22 kilonewton per meter. That's the dead load. Now for the live load, the same thing we did above is what we are going to do for the imposed load. So we have the live load on the slab multiplied by the span that we are using, that's multiplied by 4. All right, that will give us 20. The alternative way to doing this is saying you have 5 multiplied by 4 divided by 2 in 2 places. All right, so this cancels this. We have 5 multiplied by 4, so it's still the same thing that we have after all. Now what our beam is going to be subjected to is this load. So the ultimate design load for this beam will be 1.4 GK plus 1.6 QK. I believe everyone is aware of this. All right, so we have the ultimate design load, which is N, is equals to 1.4 GK plus 1.6 QK. All right, so we have 1.4 multiplied by 22.22 plus 1.6 multiplied by 20. What do we have? So if you punch your calculator, you would have 63.108. all right, so we have 63.11 kilonewton per meter. All right, so this is quite clear. All right, this is quite clear. If you have questions as to what I've done just now, you can use the comment section. I will answer to all your questions, query, and additions there. All right, so to go proper into our designs, now is the time we'll be using our BS code in addition to this that we have learned just in in a while. So we have the first thing you want to calculate would be your effective depth and also your effective width of your flanged beam. Remember, the beam you are dealing with now is a flanged beam. A flange beam. Something like this. All right. I just want to be a little straight so that we have something nice. So what we are dealing with is basically like this. So we need the effective width of this flange. We need this. So how do we obtain that? We need BF. How do we obtain the effective flange width? I'm going to show to you in the code how we do that. Effective flange width. Now, when you check your BS code, you find a clause there, clause 3.4.1.5, clause 3.4.1.5. So let's check there, 3.4.1.5. So you have to have a copy of this so that as time goes on, you can relate with whatever it is that I'm referring to. All right, 3.4, you see beams there. We have 0.1.5, which says the effective width of flanged beams. You did see that? And now we are dealing with the T-beams. We are dealing with T-beams. So we are supposed to pick this web width plus LZ over 5 or actual flange width if less. If less. So let's put that to work. It says we'll be having the web width plus LZ over 5 or actual flange width. You get that? If less, whichever is less. All right, in case you did not see that, says web width plus this LZ over 5 or actual flange width if less. I remember that our flange width is 4 meters. All right, so if whatever we obtain here is less than actual flange width, we'll be using it. All right, or if the actual flange width is less than that value, we'll be using the actual flange width. So let's put it to work. So this will be equals to 350, which is the thickness of our web, and the LZ, which is 6 meters. You can see that from the question. All right, which is 6 meters. The question says this: the support beam is simply supported over a span of 6 meters. So that's how we got that 6 meters. So this would give us 1550 mm. All right, so this is to be compared with the actual flange width. Actual flange width, which is equals to 4 meters, 4000 millimeters. All right, so whichever is less. So which is less? Obviously this. So our flange width now is equals to 1550. Therefore, BF is equals to 1550 mm. So that's cool. The next thing we want to do, like I said, is to get the effective depth. Effective depth. The effective depth is obtained for a beam by subtracting from the thickness the cover, all right, and then the diameter of links, all right, then the half of the intended reinforcement of the main reinforcement, maybe the tension reinforcement or whatever it is. So for this question, the thickness is 500 and the cover, we've been given the exposure condition to be from the question, the exposure condition is mild. So putting those things together from clause 3.3.7, 3.3.7, all right, see, we have the mild condition. The nominal cover is 25, all right, and that's how we got that. So we have 25. The links diameter, we're using 8 mm links, and then the reinforcement, you can assume a reinforcement as you're starting. If it will not have any implication on your work, fine. So we would have, since we're not given a particular reinforcement to use to adopt, so we want to use maybe 25 mm. Let's try 25 mm. 25 mm reinforcement divided by 2. So this should give us, using your calculator, 454.5. All right, so this is the effective depth. So the next thing you want to do is to check for the bending, all right? So with your K value, now we can begin our design properly. M over FCU BD square. But somebody would have a question that we have not obtained the value of our M, which is the moment. So how do you think we would obtain our moment? Everybody knows for a simply supported beam, for every simply supported beam, the maximum moment is WL square all over 8. So we have the W, which is the ultimate design load, obtained here, all right? That will be 63.11 multiplied by the length, 4 square all over 8. Oh, sorry, 6 rather, not 4, because the span of the beam is 6. All right, the support distance is what we have as 4. So we have 6. So this should give us 63.11 multiplied by 6 square divided by 8. It should give us 283, or so to say 284 kilonewton meter. So we can just come here and adopt that. 284 multiplied by 10 raised power 6. All right, the FCU according to the question is given as 40. All right, and the B is 350. If you remember, and the effective depth 454.5. 454.5 squared. All right, so the answer would be 284 multiplied by 10 raised to power 6 divided by 40 multiplied by 350 multiplied by 454.5 all squared. So that will be 0.098. Oh, now this is the issue now. I want you to pay attention. Someone would have done it just like I did here, and now we'll be in a trouble because our B is not supposed to be 350. We are dealing with a flanged section. So our flanged section will be using a flange width, not the normal web width. All right. So it's supposed to be 1550. 1550. So that's what we're supposed to have, which is 0.022. Do not make that mistake. All right, and this is supposed to be less than 0.156. Now, having done this, the next step is to check for our lever arm. All right, now the proof of this is that our K value being less than 0.156 is to say that our beam is singly reinforced. All right, so we can go for our Z value, all right, which is D in the bracket 0.5 plus the square root of 0.25 minus K over 0.9. All right, so our Z will be, and this also should be less than 0.95 D. All right, so we have D in the bracket 0.5 plus 0.25 minus the K value is 0.022 divided by 0.9. All right, so the value of this would be 0.5. So we have 0.97 D, which is quite above 0.95 D, and we have to have 0.95 D. So we have to adopt Z to be 0.95 D. So our AS, which is the area of steel, can be calculated using our usual formula, M all over 0.95 FYZ. So our moment, as we know already, is 284 kilonewton meter. All right, all over 0.95 is 0.95. Fy is 460 according to the question. All right, we have been given characteristic strength of reinforcing steel to be 460, so you want to stay with that. Multiplied by the Z is now 0.95 D, is limited to that, 0.95 D, multiplied by our effective depth, which is 454.5. Now this should give us 1507.0 millimeter square. So we can just write this millimeter square. Now, how do we provide against this value? This is the area of steel required. So we have, if you're using, for example, Y25 that we started with, the diameter of one Y25 is 491. All right, is 491 millimeter square. So you can divide what you have as your required by one area of Y25 reinforcement. I hope that is clear. So we have number of reinforcement now. Number of reinforcement or bars, whatever you want to call it, equals to 1507 over 1 Y25. This one is 1 Y25. So we have 1507 divided by 491. That's 3 Y25. Bars. But if you try to do 3 multiplied by 491, you see that you have exactly, in fact, even lesser than what you have here. So what you want to do is to increase to add 1, which is 4y25. So we can provide, let's try 4, that's 1964. Provide 4y 25 bars. Area of steel provided now will be equals to 1964 millimeter square. So this exactly is the provision for this reinforcement, for this beam. Now in the next video, I'll be showing to you how to design for shear reinforcement and also for deflection of a beam, to have a complete design of our beam element. If you have any question as touching this thing I've just done to you, shown to you, I like that you use the comment section, and I'll be there to answer to everything that you have. And in case you're new to my video, you're new to my channel, I like that you use the subscribe button, you turn on the notification bell, you get a notification as soon as I drop the next video, and then you are becoming better every day. Thank you. See you in the next video. Bye.